Ask My Instructor 15.6.61. The heat flow vector field for conducting objects is F equals negative K times the gradient of T, where T is the temperature of the object and K is a constant that depends on the material of the object. We're going to compute the outward flux of F across the 6 faces of a cube. First, we're going to find negative K times the gradient of T. Our x and y components are identical. Our z component is 0. If we take out 50 e to the negative x minus y, if we take that expression out, we're left with the vector 1, 1, 0, which tells us that at every point in the cube, the vector is pointing in the exact same direction. The only thing that changes is the magnitude. The direction that each vector is pointing in is the direction that is parallel to the xy plane and going at a diagonal across that floor of the cube. So the outward flux across a surface is F dot n, where n is the unit normal vector pointing in the outward direction. In this case, the surface is a cube, so the flux integral must be evaluated for each face of the cube. So we have 6 faces. In each case, we need to find the vector that's normal to the face. And it has to point outward from the center of the cube. And you can see that for each face, for example, the face x equals 2, the outward normal vector is just going to be 1, 0, 0, because 1, 0, 0 points in the same direction as the x-axis, which is the x-axis is perpendicular to the plane x equals 2. Now, for the plane x equals negative 2, we're pointing in the direction of the negative x-axis. And so there the unit normal vector is negative 1, 0, 0. If we were to do the ceiling of this cube, the ceiling of the cube is perpendicular to the z-axis. And so the normal vector there would be 0, 0, 1. And again, the vector must be of length 1. For the floor, it would be 0, 0, negative 1. For the face, x equals 2, y is going to run from negative 2 to 2, and z is going to run from negative 2 to 2. And as I said, the unit normal vector is going to be 1, 0, 0. If I take 1, 0, 0 and I dot that with 1, 1, 0, I'm going to get a dot product of 1. And so the result will be 50 e to the negative x minus y. If x is fixed at a value of 2, then we have 50 e to the negative 2 minus y is the dot product, and is the dot product for this face. We need to do it for all 6 faces, and I show you here my results. An interesting result is z equals 2 and z equals negative 2, where the dot product is 0. Look, I've got 1, 1, 0 dot 0, 0, 1, which is 0. But geometrically that makes sense as well. My vector field F, remember I said all those vectors are horizontal. They're all parallel to the xy plane. So there is no outward motion across the a ceiling or across the floor, because all the vectors are parallel to the ceiling and the floor. Notice that the integrand for x equals 2 and y equals 2 is identical. Well, I'm sorry, they're not identical, but follow a similar pattern. And x equals -2 and y equals -2 also follow a similar pattern. I'm going to take these results and form the integral, which will give me the outward flux for each face. Now the outward flux for the face z equals 2 and z equals -2, that outward flux is 0. If you have an integrand of 0, there's no point in integrating. You're going to get an integral, the integral evaluated with an integrand of 0 will be 0. And as we discussed before, geometrically there is no outward flux. That makes a lot of sense. Now, however, there is outward flux across the other four faces. Looking at the face x equals 2, I integrate, well, first I pull out 50e to the -2, because that's just a number, and then I integrate with respect to y, and evaluate with y going from -2 to 2. And what I get is just a number, e to the 2 minus e to the -2. Well, that's just a number. And then when I integrate with respect to z, where z runs from -2 to 2, that integral is just going to be 4. And so I've got 50 e to the -2 times this number, e to the 2 minus e to the -2, times 4. I distribute the e to the -2 into the parentheses, and also bring that 50 and multiply that by the 4, and I get an outward flux for the face x equals 2. The outward flux is 200 times 1 minus e to the -4. You might want to think about that for a minute. 1 minus e to the -4. E to the -4 is about 1 over 81. So this is close to 200. So certainly a positive outward flux for the face x equals 2. What about the face x equals -2? Let's find that outward flux. Again, I pull out, in this case, I pull out 50e to the 2. And then I integrate and evaluate with respect to y. And then integrate and evaluate with respect to z. And this time I have 200 times 1 minus e to the positive 4. Or now, what kind of number is that? Well, e to the 4, well, saying it's around 81 is a bit of a stretch, because we know that e is about 2.7, and I'm basing this on a very rough estimate of e being about 3. 3 to the 4th is 81. But anyway, it's a very negative number, and I'm multiplying that times 200. And so in this case, for the face x equals -2, for that face, I have a negative outward flux. And doing this for all the faces, this is what I got. Summing up the outward flux across each face, I get a total outward flux of 800 minus 400 times e to the 4th minus 400 e to the -4th. And that would be my total outward flux across the surface of the cube for this vector field.